Okay, good afternoon. Welcome back. If you're coming back, or if you're for the first time, welcome to Stream 1 Water on Day 2. My name is Peter Cox, and I'm a board member with the EOCP. So we are fortunate now to have Jamie Eichenberger. His topic is FAVAD, the effect pressure has on water leakage. Jamie is the president and owner of Icon Services and lives in Victoria. In recent years, Jamie has aligned himself with key players of the IWA, International Water Association Group, and specifically with Water Loss Control Committee. Implementing the best practices as adopted by the AWWA has been the first and foremost for Icon Services. He's formed a relationship with the majority of municipalities in both BC and Alberta, and particularly in the Lower Mainland and Vancouver Island, where he lives. He is the past president of the Municipal Services Association, support of PWA, BC, and is a recognized EOCP instructor. Jamie keeps in the forefront of issues surrounding the utility industry relating to communities. So please help me in welcoming Jamie. Thank you.
Hello. Thank you very much for the introduction. Am I on screen? Hello.
Yeah, it's all working. Go ahead.
Oh, it's all on? Okay, thanks very much. Thank you for the introduction. Appreciate it. I thought that Brandon's presentation knocked it out of the park. That's a lot of big metal and a lot of big holes. Exciting to be around. I'm gonna ask some questions, but to start off, I'm gonna determine FAVAD is kind of a terminology that I don't think a lot of people will have come across just yet. It's fairly new to the water loss community, and I'm going to just hang on to that acronym till a little bit further into the presentation. The key for me, my hope, is to pass on the tie between leakage and pressure. I'm going to show you a handful of examples from around the world and some Canadian examples on pressure management. We're going to talk about the audits and balances that are being used to create ILI. So ILI is the Infrastructure Leakage Index. If you followed AWWA's M36 manual, which discusses leak detection, ILI is the terminology we're using instead of percentage of loss. And we kind of got started with that back in around early 2000s. Carl and Earl, again, more acronyms. And if you look at your handout, I've given everybody a cheat sheet so that you can follow along if I start talking too quickly. FAVAD we'll get to, as I say, a little later into the conversation. And then at the end, I've got a list of resources that I think you'll find quite helpful. And I'm going to try and fly through this as quickly as I can. So I think instead of us having a bunch of question and answer throughout, maybe we'll just go to a midpoint or an endpoint and cover off questions. So let's quickly look at leakage and try and understand what we're talking about. Generally speaking, if we're looking at a consultant like myself, we're usually talking about underground pipeline leak detection. What I want to point out is above ground, below ground, large leak or small leak, it all falls into a category of leakage. Whether they're findable or unfindable often depends not only on the user, but it's usually the equipment or the materials we're working with. And it gets very complicated with the new materials we're sticking in the ground. There is argument about naturally occurring and man-made, and regardless, leakage is leakage. But what we are finding is that there are examples of poorly installed or improperly installed. And there's also a lot to be said for some naturally occurring situations. I remember a project in Manitoba and Winnipeg in the middle of winter. The cast iron water mains had the frost go quite a ways past it. And as the frost worked its way out of the ground, it was creating something in the neighborhood of 400 leaks a month in the early spring. Frost heaving pipe out of the ground. Those leaks were usually easy to find because the back of the cast iron was breaking. They were big leaks. But we also had in Saskatoon a newfangled plastic water service that was being taken out to the mains, and the instructions weren't given to put the inserts into the plastic when we used the compression fitting at the main. So we ended up with city streets with water services popping off because we didn't put the inserts in when we were supposed to. And then we're going to have a quick discussion about how expensive water is, or whether we consider it inexpensive. In the handout that I've given you on the first page, there's a calculation in the infrastructure leakage index manual that lets you read through and figure out if your system can look at water as being inexpensive or whether it's now moving into the expensive category. And as far as I can tell in BC, with the water treatment processes that we're having to put water through, almost none of it is what we could call cheap anymore. To wrap your head around water leakage, I threw a stat together for a coastal water trade show here about 2 years ago. And this was one of the slides I presented. One of the folks in the crowd actually pointed out that instead of 12 days at a liter per second getting us 1,000 cubic meters, he said if it ran for the month, it would cover his salary and his partners in the municipality they were with, because they were up over $1 a cubic meter at wholesale. We often don't take a look at the passing hydrant or the leaky valve as being a big deal, but when it's 24/7, it becomes a factor. Here's some of the examples. And if we start on the left-hand side, you're going to hear me talk a lot about background leakage in this presentation. The big part about FAVAD, it's there to help us understand in the size of your municipality with the amount of water mains and the amount of services, how much leakage can be attributed to this background leakage that's more or less unfindable with the technologies that we have. If we look at the middle section, we've got the unreported leakage. So if your group doesn't have a proactive water leak detection program, generally speaking, we're waiting for that center one to become the right-hand one. In other words, as a leak progresses and grows bigger, it will ultimately find its path of least resistance, which is often up to the surface. If you take a look at the tools that we have at the bottom to go at mitigation, in every instance, if we do some work with pressure, we're going to gain some ground on all categories of leakage. And that's important to remember throughout this presentation. Thanks. We often have in North America a fairly robust pressure goal, and oftentimes it's satisfying fire flow requirements and making sure that the pressure at the mayor's house is really good for a shower. How much is too much? How much is a problem? How much is too little? And how do we control this pressure? I know that in North Vancouver, we had some zones that were, I believe, 40 at the top, and I think almost 130 PSI at the bottom. Big hillside communities are going to have to wrestle with that because their head pressure gets overwhelming. I think in Gold River, we had a couple of spots up in the, right up by the water tower that were down below 40 PSI, and they needed to put booster stations in to keep people happy up there. But their system was controlled anywhere from 40 to 120 PSI. And they had one small district down at the river at the bottom that had a PRV and did restrict pressures into their commercial district. But for the most part, it was all head pressure off the reservoir. And if we take a look at what's affected at a household, you'll find that it's often just the shower and the lawn sprinkler out the back. If you think about it, the sink, the washing machine, the tub, they all will fill based on whether you've got 40 PSI or 10 PSI. It just will take a little longer. The spots where it's really evident is when we're standing in that shower with a water saver shower head. Now this is going to take a little explaining. I've got the fixed outlet pressure, and then I have the modulated pressure. Let's have a quick discussion about the fixed outlet. This is standard in the majority of the municipalities I work with. We'll have an outlet pressure, and in this example, we don't have to actually put a meter's head on this, but it looks like that's probably what this diagram is reflecting. Got lots of head pressure from the reservoir, but it goes through a PRV. And as the flow down in the bottom left corner, as the flow increases after 6 a.m., we get our peaks. We get one, maybe two peaks through the day. And if you'll notice, at the critical point in the system, so the home that has the toughest time maintaining a good average pressure, he drops from 45 down to 20 when everybody's using it. So when that flow goes up, the pressure goes down, and that's generally what we're setting the PRV to satisfy. You can see the PRV outlet is set at 45, and we have 45 in the middle of the night up at the critical node, but it drops back down to 20 when everybody's using. And we've solved a lot of this trouble with continuous amount of looping in most systems. Generally, we often have a critical node at the end of a dead-end street that becomes an issue, but not just for water quality, but for pressure supply, or flow supply, I mean. But when we go to a modulated PRV, where we're actually going to try and take the peak pressures off the system, you'll notice that as the flow goes up, as the flow goes up in the bottom left, after our 6 a.m. wake up, everybody starts using, the pressure outlet gains pressure based on that flow. And you'll notice that at the critical point, they pretty much always see the worst case scenario that they're going to see through the day. So if we can satisfy that critical point and make sure it's above that 20, let's call it meters head, everybody's happy. And this makes a dramatic difference when it comes to leak work. And you'll see that in the next couple of slides. Oops. This is a typical diurnal cycle or a daily chart of our flows and pressures. And if you take a look at the black line at the top, the pressure is up substantially in the middle of the night. Quite often when we're looking at minimum night flows, we're going out somewhere between 2 and 4 a.m. to measure those. And you can see they've got some arrows on this data to show what the minimum night consumptions are. And you'll see the pressures are always at their maximum. And one thing you may notice in your system is almost always when you come to work in the morning, somebody's reporting a leak. It's often because this maximum pressure is when the system fails more often. And we'll get to the main reason for those extra pressure situations a little later on in the presentation. But let's have a look at the light blue is typical consumption through a typical day. The red is an indication of the leakage that we can actually go and reduce in that daily flow. But there's that purple section, and I mentioned earlier, background leakage. That's that seeping O-ring or the old gate valve with the bad packing gland, things that we're having trouble identifying and getting out of the system. That background leakage is going to be there, and it's going to be a factor in everybody's system. But the proactive leakage program is what would go after that red. I wanted to give you some history on this. Back in the late 80s, early 90s, the UK went through a multiple year drought, and they ended up privatizing the water systems. So it turned out that they had about 5 major water companies created. Thames Water, what's the name of the other ones? I'm struggling to remember them, but they were trucking water to reservoirs because the systems were leaking so badly they couldn't supply water to every street all the time. When they privatized, they started looking at any alternatives they had to solve the problem, and the first thing they went after was turning the pressure down in the overall system. The technology ran around the world, and we started putting controllers on a lot of PRVs, and in some of the cases, Brazil, for example, they had astronomical amount of leakage, and they started applying these newfound technologies in a lot of the systems. The one fellow that I'd worked with a consulting firm in Canada was a fellow by the name of Julian Thornton. These are some of his slides that I've borrowed, showing some of the work that they were doing back in the 90s when we were learning what we could do to mitigate leakage. The South African work was done with a buddy of Julian's, a fellow by the name of Mark Shepard. And if you remember, I don't know, probably 4 or 5 years ago, there was a countdown in Cape Town as to when their reservoir was going to run out of water. And the guy who rode in on the White Knight, or the White Knight that rode in on the Stallion, was Mark Shepard. And what they did is they threw a bunch of pressure controllers on all of the PRVs going into Cape Town and gained a bunch of payback. All of a sudden, we were getting down to the less than 30 days worldwide news, and then all of a sudden we didn't hear about it anymore. And the big deal was that they put the pressure controllers in place and started reducing the amount that was going out through the leakage in the system. This is an example of a water savings when they were just doing a test run to see how much they could turn the pressure down. And you can see they took a 6-day period where they just notched it down a little wee bit. And just the little bit that they had turned the pressure down over that 6-day period saved them, it's something in the neighborhood of 2.5 million gallons a day. Big systems though. This is another very big system down in Sao Paulo. 3.4 million gallons a day. It's nothing to sneeze at when it's only, you won't be able to read it all that easily, but the size of this zone is only about, 63.7 kilometers with about 53,000 population, about 13,000 services. So it's not that massive, but it certainly was a big savings. That's my buddy Julian there on the right with laptop hooked up. And there's some of the PRVs that they were dropping in the Brazilian market. One of the benefits of pressure management has proven to be how much it stabilizes the water hammer and peaks and valleys. The blue indicates after a controller was put in place, and you can see in the red, there are some peaks which relate to water hammer, which ultimately leads to break frequencies. And they were seeing a substantial savings in reduction in breaks. And we're going to talk a little bit further down the road here about how this has become a more significant dollar figure savings than the actual water saved in the leakage. You'll notice that this PRV station is very well guarded. And I remember Julian saying that when they visited this site, the warning from the staff was that if they didn't let the police know that they were going into this area, the motion sensors were going to have armed police show up because they didn't want anything to happen to this PRV station. And that's a testament to how important this water work was going to be to Durban. And they put in a whole series of new stations like this, big PRVs with full control. And there's my buddy Julian again on another laptop. This is where they're using a remote node modulation, meaning they have a sensor at the critical node, which feeds back to the PRVs to help with the pressure outlet settings. And again, these are savings in mains breaks over the window of time that they had put these controllers in. And this is another example of the service breaks. All of it, very substantial reductions. Down in the Bahamas, Julian again there on the right, trying to figure out how tall he is. I guess the water had been pretty low in that reservoir. They were putting in flow controllers so that they could make sure that they didn't have storage overflow. And these big Venturi meters were coming out and PRVs were being put in. Now we're going to switch over to Canada. And the Halifax system has been at it for quite a while. They were learning from that IWA group. They had a fellow by the name of Ken Brothers who joined the International Water Association Water Loss Control Committee. And he started working very hard at implementing this because Halifax had just merged 3 cities. They had brought Dartmouth, Central Halifax, and the outlying regional district all under one roof. And they were looking to get a handle on the volume of loss that they had, because now it was the regional district that was tying into these three joined cities, and they needed to get a cap on what was going out of that reservoir. Some pretty substantial savings. And the best part, according to Reed Campbell, who put this together, the best part was the amount of information that they were getting, the amount of data, the way in which they could operate their system, manage their system better. This is the kind of reduction they had in their the infrastructure leakage index. They were dropping from as high, I think the west was, it wasn't Dartmouth. I'm trying to remember how this worked. One of them was quite a bit worse than the others. It still maintained that throughout, but they were gaining ground. And when we get to the FAVAD discussion, remember that red line, that's the one that stands out quite a bit. But they were making progress. But they got to a point where they could get certain districts down to an ILI that was around 2.5. And in layman's terms, the way you would look at ILI is if you're at 2.5, that means you're 2.5 times worse than a gold star. If you're a 1, you're getting the job done. If you're an 8, you're 8 times worse than you could be. So the scale, and because we look at every drop and where it's going, the scale is usable in large and small cities throughout, and we'll come up with the same numbers. ELL is a calculation we're not going to talk about this time around, but what Halifax was striving for was what is the economic level of leakage, and based on how much their water cost and how much it cost for them to go out and try and mitigate the water loss, they wanted to come up with that calculation. What is the economic level of leakage and how low could they go? The amount that they could go low was restricted before they figured out this terminology that we're using called FAVAD. And we're going to get to that here very shortly. This is a project I did some work on with a group out of Toronto. East York is one of the 5 cities that were merged together in the city of Toronto. And it had 3 feeds off of their metro water line. And the 3 feeds did not have any PRV controllers. They just had Venturi meters. And the goal was to put PRVs in and control the flow into this system, which maybe had 54, I think it was 54 kilometers of pipe, and almost all of it cast iron or steel of some kind. We didn't see a dramatic difference in the flows, but we did change the pressure. If you look at the light green line is the pressure settings we put into the controllers versus the dark green line, which was where the pressure was going to in their normal diurnal cycles. We had 5 years after this installation, they were averaging something like, before the installation, they were averaging something like 5 leaks per year on the mains, and then a myriad of service leaks. And they went to 0 leaks on mains for 5 years. So we made a big difference on the cast iron in that system with the pressure management. And I was involved in trying to get these big turkeys stuffed into the little chambers. We were trying to decide whether using the old chambers was a money saver for the city if we put all this technology into the old boxes. And I got to tell you, it was all we could do to stuff that bad boy in there. And if you look at that little gray fitting, that's one of those, I think they call it a deflector coupling. And it's basically got a big rubber boot. And there was about a 3/4 of an inch deflection in the pipe that was coming in from one end of this chamber to the other end of the chamber. And that little rubber gasket was supposed to help us. Well, man, you should have seen the guys trying to get torque on those bolts to get in there, tighten that one up. It was not easy. But we did get it closed up and it didn't leak. This is friends of mine up in Gold River. I go up about every 5 years to do a leak sweep. And I think you can see about every 5 years, we seem to knock that January flow down pretty dramatically. We usually do it at the tail end of the year, October, November. And one thing you can see is that within a year, this town tends to fight its way right back up to the same amount of leakage. And here's where I would make the point that the system will self-regulate pressure. It's going to go and create enough leakage that it's comfortable. So if we don't fix the leaks and then moderate the pressures, we're just going to have this stalemate where we go back to the same situation, leakage over and over again. If we can apply on proactive leakage with a proactive pressure management, we're going to start to win the war. All right, here we go. Back to the original slide that I think is probably one of the more important ones, and you have it in your handout as well. This is the best way to understand what we're trying to achieve. If, for example, we could just bring that night pressure down, so that might be a timed pressure that we would put in front of that PRV to tell it that we don't need maximum pressure in the middle of the night, then we can put a controller in that would do that. What we hope to do is have enough measurement that we know how much water the system should be using. With, if we're not fully metered, we come up with the measurement that says our flow rates should be this on a daily cycle of flow. And we work towards driving this number down so that our red and our purple is less and less. And we just have the normal consumption with the least amount of pressure on the system. So in your cheat sheets, you're going to see that we've been talking about that international, or the infrastructure leakage index. The next two that we're going to spend quite a bit of time talking about here is the unavoidable annual real leakage, so that purple, the current annual real leakage, which would be the red included with the purple. We're going to talk about district metered areas. We're going to talk about pressure managed areas, and then we'll get to FAVAD here. I'm going to show you a water balance. This is, if you look at the latest version of the M36 manual from AWWA, this is a representation of the data that you will fill in. So the system input volume, whether you're buying your water from somebody or whether you're manufacturing your own, you put that in one of the columns that gets split with authorized consumption or water losses. And what we're looking at is revenue water or non-revenue water. So our target is to create a smaller version of non-revenue than especially what's in this diagram. We have billed authorized consumption and unbilled authorized. I'll help you break those into categories here in the next round. Apparent loss and real loss. If you can imagine, apparent loss is exactly that. It looks like it's missing, but it actually isn't. Real loss is where it's leaving the pipe. So let's have a look. Build metered consumption, that's pretty obvious. And then build unmetered consumption. Now, we've got cities that don't have residential metered. We have cities that are fully metered, and it can be any combination of those two for this revenue water stream. Then we get to typically what's involved in the municipality itself. Unbilled metered consumption, so whether you send the mayor a bill for what the city hall uses, whether we have unbilled, unmetered out in the ballparks and city parks, those are all authorized consumptions, whether they be metered or not metered.
So Jamie, Peter here, we've got 10 minutes to the end of the presentation.
Oh, okay.
Good.
I can talk a little bit faster and we'll get there.
Great. Thanks so much, Jamie.
Yep, thanks. Unauthorized consumption, that's of course theft. And it can be anything from somebody hooking up to your hydrants and filling their water trucks, or just somebody who knows how to tap a water main before the meter. And then we have meter inaccuracies. And up until the point where we stopped using, well, we're still using some displacement meters. We had a lot of tired meters that would lose the bottom end. So low flows often didn't register in meters, and that falls into the apparent loss category. And unless we kept a metering program up to snuff, that apparent loss calculation got bigger and bigger. And then this is the stuff that I've been chasing for many years. Leakage on the transmission system, leakage on the distribution, confirming that we have leakage at reservoirs. That became something we weren't aware of back in the day, where we'd shut off the reservoir and it would still drop in elevation. And we had overflows that were not measured into our calculations for real loss. We weren't going to get paid for that stuff. Leakage on service connections up to the metering point. And if we didn't have meters, then that meant that a municipality is suffering all of the homeowners' piping as well as their own. And that can become a big issue. But that is a 100% breakdown of all the water that you use. And we put this into a yearly calculation. There's a freeware software available through AWWA. You can go online, sign up for it, and they'll send it to you for free. And the newest version has an adaptation to FAVAD, which we're going to get to here in a sec. If you'll notice, it's very hard to read the center of that blue box, but it says current annual real loss. What we have is a box with 4 ways in which we can lessen that current annual real loss. Pressure management at the top, an active leakage program, pipe replacement, renewal, rehab, and then speed and quality of our repairs. If we repair it and then have to come back and repair it again on the same repair, that's not closing the blue box down much. But what you'll notice is the pressure management has the unavoidable attached to the top. If we turn down the pressure, that leakage, the unavoidable leakage that we can't find, will lose less water. Ooh, I said that without stumbling. Both the leakage rate that we have and the unavoidable leakage rate that we have will both be benefited turning down pressure to make this box smaller. And then we can apply the other 3 as we see fit. And that's where Halifax realized pressure management. And I think they have something in the neighborhood of 37 pressure management zones in their effort to eliminate leakage. They apply all 4 of these arrows, but apply pressure to all zones. And then the other 3 arrows are as they see fit after turning pressure down on all of them. All right. Unavoidable annual real loss is a calculation that's been refined by doing this. We take a look at the mains length, the number of connections, and then the third one is the tricky one, length of underground, whether it be private or to the curb stop. That's depends where your meter is, or if you have a meter. In the prairies, of course, the meters are often inside the houses. And in Vancouver, Victoria, they're all out at the curb. So we can refine the measurements for the unavoidable by looking specifically at your system, measuring all of these things, including the average zone pressures. Now, take a look at that. Fixed and variable area leakage paths. We're almost there, kids. If you take a look at a solid pipe, a rigid pipe, that water, as we turn pressure down, will only decrease by a certain amount. A very specific line that's almost linear there. You can see the top right chart. But when we have flexible pipe, if you can imagine that crack with more pressure, the area that opens up to discharge increases. So what they've figured out here in the last few years is that they have to put a different calculation in if it's plastic or flexible pipe. They have to put a P1.5 versus a P0.5 in the calculation for determining the volume of loss. So the sum of what you have in your system. So as cities are growing, we're putting more and more plastic in, and we're starting to recognize we have to put a different calculation in for the volume of loss that we're not going to be able to find in the unavoidable. And Halifax jumped on this because that allowed them to recognize a lot of the districts where they weren't achieving something as good as 2.5 was because they had a lot of plastic in that system, and they had to change the calculation so that they could work in these smaller districts and refine it to the point where they could chase the right areas for the right leakage. So big deal here, and this is the terminology. Fixed and variable area discharges are made up of how much fixed rigid pipe you have in your system or variable flexible pipe that you have in your system. I was working on Black Diamond in Alberta, and we determined that they have 78% flexible pipe in their system. Pressure management is going to be a massive tool for them in their fight against the loss rates that they have. So again, flexible pipe versus the rigid pipe, it changes the volume of water that goes out as we turn the pressure down. And that's the relationship between pressure and flow. This is a chart done by Alan Lambert. He's the guy who was the guru at the top of the pile for the Water Loss Control Committee with IWA. He just retired this year, but we squeezed a little bit more information out of him. And he did the last presentation for the IWA water loss conference that was held in the US. I think it was 2018 or 19. And what we can see here is the blue line with the 0% rigid pipe is most affected by a pressure reduction. So that plastic in the system, if we just turn it down a little bit, we're going to see a big savings in water loss. And because we have put this FAVAD calculation in, we can now do any sized system. So if you have pressure zones that have less than 5,000 services in them, 3 years ago, the AWWA ILI calculations wouldn't work for you because that would be too small for them to do the calculation. It's too close to the end of the bar graph. What we need to do now is look at small pressure zones individually, and we can get this UARL and CARL calculation for each zone in your system. All right, here's what we can do. Have a look at your system, have a measurement, get a calculation done off your GIS to see what is rigid and what's flexible. Guesstimates are okay, but the more refined, the better. Measure where your critical nodes are. The model will tell you one thing, but you may want to go out and put some pressure loggers in the field just to confirm it. Understand what your PRV or head pressure is and what those fixed outlet pressures are. And perhaps you do an experiment like that 6-day experiment that we did down in Brazil. I have put this in your handout. Leak Suite Library is a culmination of all the stuff that Alan Lambert had put together. That's on his website. The WLR&A, which stands for Water Loss Research and Analysis, is a combination of Alan and his daughter Kate that are keeping the information out there and available. AWWA have just put out a new M36 manual, and that has a ability to apply the FAVAD. And then I've linked my website to Alan's website, and I've actually got all of his online training available through me for the Canadian market. So what I'd like to point out, anyone that's interested in getting any of the 3 online training that we have available, anybody that's attended this just needs to contact me, and we will come up with a way for you to get involved with the Water Balances Essentials, which is the first of a group of 3. I also have the NRC FCM manual for the water loss. National Research Council teamed up with the Federation of Canadian Municipalities in the early 2000s, and I think they completed this in somewhere between 2005 and 2007, and then promptly shut their website down, I think in 2008 or 9. Luckily, I printed off the best part for the water loss management, and I have that available and can forward it out to anyone that would like to see it. So EOCP has approved the Water Balances Essentials for a 0.6. Typically, it's going to take you about 5 days on your own time, but lots of really good information that I've skimmed over here today. I'd like to thank you, and I hopefully have kept it on time.
Yeah, thanks so much, Jamie. That was great. Just one quick question about relining pipes, like with CIPP, to help reduce loss. Is this a Band-Aid, or does this cause problems down the road, was what the question.
Nope. There's lots of room for rehab to work at mitigating pipe leakage. There's a lot of good materials out there now that are making a difference. I know that the CIPP has really done its most of its time in the sewer side, and one of the tricky bits with pressure pipe is making sure we get a really good, clean cut in with services. But it has merit for sure.
Appreciate your insight in that, Jamie. Thank you, and everybody, thanks for joining the session today. Jamie's got his contact information up there, and of course the presentation was also put in the chat. So thanks everybody, and you got a 10-minute break, and we'll be back at 4 o'clock for our last session. Thanks, Jamie. Thanks everybody.
Great. Thanks a lot.